I thought he was joking at first, but he was serious. He said, imagine that an electron's path through space and time, what we call a world line, doesn't just go forward in time. What if it goes backward too? What if it zigzags back and forth through time like a huge tangled knot? When you take a slice through this knot at any particular moment, you'd see the line cut many times. Each time you cut it, that's an electron at that moment. But here's the kicker. Half the time, the electron would be moving forward through time, and half the time it would be moving backward. And when it's moving backward through time, it would look like it has the opposite charge. It would look like a positron. Now, I didn't buy the whole one electron in the universe idea. That's got problems. The biggest problem is that there should be equal numbers of electrons and positrons if that were true, and we don't see that. We see way more electrons than positrons. Wheeler even suggested maybe all the positrons are hiding inside protons, but that doesn't really work either. But you know what? I stole his idea anyway. Not the one electron universe part, but the idea that a positron could be thought of as an electron going backward in time. That insight turned out to be incredibly useful. Let me explain what I mean by going backward in time, because I'm not talking about time travel in the science fiction sense. I'm talking about a mathematical description that makes the calculations work out beautifully. See, when we write down the equations for how particles behave, we get solutions that seem strange. They seem to describe particles with negative energy moving backward through time. For years, people didn't know what to make of these solutions, but then we realized these aren't weird, unphysical solutions we should throw away. They're describing real particles. They're describing antiparticles. Think about it this way. When a photon of light creates an electron-positron pair out of nothing, we usually say the photon's energy got converted into matter. But you could equally well say that an electron was traveling along, got hit by a photon, and started traveling backward in time. When it's going backward in time, we see it as a positron. Same event, different description, and both descriptions are completely equivalent mathematically. When an electron and positron annihilate each other and turn into light, we usually say the matter got converted to energy. But you could say an electron was traveling forward in time, then got scattered backward in time by interacting with light. The annihilation is just the turning point where the electron reverses its direction through time. Now, why would we want to think about it this way? Because it makes the math so much simpler. See, in quantum theory, to calculate the probability that something happens, you have to consider every possible way it could happen, every single path the particles could take, and you add up little arrows for each path, and when you're done adding all these arrows, you square the length of the final arrow, and that gives you the probability. Let me give you an example. Suppose two electrons are approaching each other. They're going to scatter off each other because they're both negatively charged. How does that happen? Well, they exchange a photon. One electron emits a photon, the other absorbs it, and they both change direction. But here's where it gets interesting. That photon they exchange, it's what we call a virtual photon. It doesn't have to follow the normal rules. It doesn't even have to travel at the speed of light. It's just a mathematical bookkeeping device for the interaction. Now, you could draw this process as one electron emitting a photon that travels to the other electron. But you could also think of it differently. You could think of it as one electron emitting a photon and a positron at the same time. The positron travels backward in time to where the other electron is and annihilates with it, creating another photon. These two photons then do whatever photons do. Sounds more complicated, right? But mathematically, it's exactly the same process. The Feynman diagram is the same. One diagram represents multiple physical interpretations. This is what's so beautiful about this time reversal idea. It cuts down on the number of different processes we have to keep track of. Instead of having separate rules for particle creation, particle annihilation, particle scattering, and antiparticle scattering, we just have particles that can be scattered forward or backward in time. That's it. 4 types of processes become one. The math becomes simpler, and the predictions stay exactly the same. Now, I developed these diagrams, which people now call Feynman diagrams, to help visualize and calculate these processes. In these diagrams, time usually runs from bottom to top. A line going upward represents a particle moving forward in time. A line going downward represents an antiparticle, or equivalently, a particle moving backward in time. When lines meet at a point, that's an interaction. An electron can emit or absorb a photon. That's it. That's the basic action. Every complicated process in quantum electrodynamics can be built up from these simple pieces. You draw all the possible diagrams for a process, calculate an arrow for each one, add them all up, and you get your answer. And it works. Boy, does it work. We can calculate the magnetic moment of the electron to incredible precision, and it matches what we measure in experiments. 10 decimal places. That's like measuring the distance from New York to Los Angeles to within the width of a human hair. But here's something that bothers people, and it should bother you too. What does it really mean for a particle to go backward in time? Is that actually what's happening? I don't know. Nobody knows. The theory doesn't tell us what's really going on. It just tells us how to calculate what we'll observe, and the calculations work, so we keep using them. You see, in quantum mechanics, we've learned that we can't always answer the question, what's really happening? We can only calculate probabilities for what we'll observe if we make a measurement. Before we measure, we can't even say the particle has a definite position or momentum. It's in some kind of superposition of all possibilities. And that's weird. It bothers me as much as it bothers you, but nature doesn't care if we're bothered. Nature is what she is, and she's going to do what she's going to do, whether we like it or not. Our job as physicists is to find mathematical descriptions that match what we observe. And quantum electrodynamics does that better than any other theory we have. Let me tell you about another strange thing. When I calculate these diagrams, I have to include what we call virtual particles. These are particles that appear temporarily during an interaction and then disappear. They violate energy conservation, but only for a very short time. The uncertainty principle lets them get away with it. The more energy they borrow, the shorter time they can exist. So when two electrons scatter off each other, the photon they exchange is virtual. It pops into existence, travels between the electrons, and disappears. You might say, wait, that's not a real photon then. Why are we including it in our calculations? Because we have to. If we don't include these virtual particles, our calculations don't match experiment. Nature is telling us these virtual particles are part of the story, even though we can never observe them directly. And here's where it gets really wild. You can have virtual electron-positron pairs popping in and out of existence all the time, everywhere. A photon travels along, and for a brief moment it turns into an electron-positron pair, then they annihilate back into a photon. Or an electron travels along, and for a moment it emits a photon, and then reabsorbs it. All these processes are happening all the time. We call it quantum fluctuation or vacuum fluctuation. The vacuum isn't really empty. It's seething with virtual particles popping in and out of existence. You might think this is all just mathematical fantasy, but these virtual particles have real measurable effects. They change the energy levels of atoms very slightly. We can measure this change called the Lamb shift, and it matches our calculations exactly. The virtual particles are doing something, even though we can't see them directly. Now, when I draw a Feynman diagram with a virtual electron-positron pair, I could draw the positron as a line going forward in time, or I could draw it as an electron going backward in time. Same diagram, different interpretation. And this is where the time reversal idea becomes really useful. It lets me think about all these processes in a unified way. Let me give you another example. Suppose a photon creates an electron-positron pair. I can think of this as the photon creates two particles, an electron and a positron, which fly apart. Or I can think of it as there was an electron traveling along. It got hit by a photon and scattered backward in time. And now where the photon hit, we see both the electron before the collision and the electron after the collision going backward in time, which looks like a positron. Both descriptions give the same answer. The mathematical formalism doesn't care which interpretation you use. It just churns out numbers, and those numbers match what we see in experiments. But as humans, we like to have a picture in our heads of what's happening, and sometimes the time reversal picture makes things clearer, at least mathematically. Here's something else that's strange. In these diagrams, the photon can be emitted before it's absorbed, or absorbed before it's emitted. Time ordering doesn't matter in the quantum world the way it does in our everyday experience. We have to sum over all possible time orderings of the events. The photon goes from point A to point B, but we can't say whether it left A first and then arrived at B, or arrived at B first and then left A. Both possibilities contribute to the final answer. This sounds completely crazy, I know. How can something arrive before it left? But remember, we're dealing with virtual photons here, not real ones. They don't follow the usual rules. They exist only in the calculation, only as a way of keeping track of how the interaction works. And when we add up all the possibilities, including all the different time orderings, we get the right answer. Now, you might be wondering, does any of this have practical applications? Well, quantum electrodynamics is the basis for understanding how light interacts with matter, which is the basis for lasers, transistors, all of modern electronics, photovoltaics, LED lights, you name it. Every time you use your phone or computer, you're relying on our understanding of QED. So yes, it's incredibly practical, even if the underlying theory sounds insane. But beyond that, this way of thinking about antiparticles as time-reversed particles has been incredibly fruitful. It's part of how we understand the standard model of particle physics. Every particle has an antiparticle. Quarks have antiquarks. Neutrinos have antineutrinos. The photon is its own antiparticle because it looks the same going forward or backward in time. This pattern makes sense in the framework where antiparticles are particles going backward in time. And here's something that blows my mind. This whole framework predicts that particles and antiparticles should be created and destroyed in pairs. You can't create just an electron without creating a positron too, unless you're converting another particle into an electron. This is related to charge conservation. And indeed, that's exactly what we see in nature. Pair production and pair annihilation always happen together. The theory predicted it, and nature does it. But I want to be honest with you, we don't really understand what time is. We don't understand why there's an arrow of time, why we remember the past but not the future, why entropy increases. These are deep questions that quantum electrodynamics doesn't answer. QED just gives us a set of rules for calculating probabilities. It tells us that mathematically, we can treat antiparticles as particles going backward in time, and this makes the calculations work out. But whether particles are actually going backward in time, in some deep sense, I can't tell you. The theory doesn't answer that question. What I can tell you is that nature is far stranger than we ever imagined. Particles that go backward in time, virtual particles popping in and out of existence, photons that don't know whether they were emitted before they were absorbed. And yet, we can calculate all of this, and our calculations match reality to an astounding precision. This is what physics is all about. Not pretending we understand things we don't understand, but finding mathematical tools that let us predict what will happen. And quantum electrodynamics is the best tool we have for understanding light and matter. It's weird, it's counterintuitive, it seems impossible, but it works, and that's what matters. You know, people always want to know what's really going on, what's really real, and I wish I could tell you, but the honest truth is we don't know. We have this mathematical framework that makes predictions, and the predictions are right. Maybe someday someone will come up with a deeper theory that explains why QED works, that gives us a clearer picture of what's really happening. Until then, we work with what we have, and what we have is pretty remarkable. We can describe the interaction of light and matter with incredible accuracy. We can understand how atoms work, how lasers work, how light bounces off mirrors, how electrons scatter off each other. All from these simple rules about electrons and photons and the arrows we draw to represent them. So does light really go backward in time? In the mathematical sense, yes. The equations allow for it, and it's a useful way to think about certain processes. In a physical sense, I don't know. Maybe that question doesn't even make sense. What I do know is that this framework works, and it's given us deep insights into how nature operates at the smallest scales. And that's the beauty and the frustration of physics. We get these powerful mathematical tools that let us predict and control nature, but we're always left with deeper questions about what it all means. And maybe that's okay. Maybe the meaning is in the search itself, in the struggle to understand, in the wonder of discovering that nature is so much stranger and more beautiful than we ever imagined. That's quantum electrodynamics. That's the strange theory of light and matter. And as strange as it is, it's the best description we have of how the universe works at the quantum level. Make of it what you will.